Hi, I am Gilles Calabot. I'm part of the research group DRUMCO. In DRUMCO, one of our main research topics is low power wireless communication, where we try to optimize the energy efficiency of Internet of Things devices. These devices are deployed in different environments with different channel dynamics. The difference in channel dynamics can be seen here in these three projects where we are involved with. At the left is a project where we would detect if if buoys were drifting from its intended position. Due to being on open water, the channel dynamic is quite stable. On the other hand, at the right, there we placed some nodes inside a tunnel, so we could monitor some construction-related parameters. They were working on the tunnel, so it was important to detect movement in the construction to ensure the safety of the crew as well as the passing traffic. This environment has a lot of dynamics due to the traffic. And the other project in the middle, we monitor some vital signs of sheep. While they are confined to one area, sheep tend to move around and so thereby introducing some dynamics in the channel. To be able to adapt to different propagation conditions, LoRaWAN, the protocol under investigation, changes its data rate. So decreasing the data rate ensures that the signal has more energy per bit, and therefore the signal could reach further. This is done by changing the spreading factor. In LoRaWAN, the signal is modulated by sweeping. As you can see here, this is the frequency and this is the time, and LoRaWAN sweeps across the bandwidth. The spreading factor determines how long it takes to reach or to sweep across that specific bandwidth. So close to the gateway, a low spreading factor of 7 can be used, which has a higher data rate, while for longer ranges, we would use spreading factor 12 to reach further. By increasing the spreading factor by 1, so going from spreading factor 7 to spreading factor 8, for instance, the symbol time is doubled, so the energy required to send the same payload size is approximately doubled as well. In LoRaWAN, the SNR is used as a criteria to determine the link quality. The minimal required SNR to be able to demodulate the symbols depends on the spreading factor. A higher spreading factor ensures that we could demodulate the signal with lower SNRs. By changing the spreading factor, we actually change the SNR demodulation floor of the receiver. As recommended in the LoRaWAN specification, the maximum of 20 consecutive packets is used to determine the SNR margin with respect to the SNR demodulation floor. In case the margin is positive, this means that we could potentially lower the spreading factor or transmit power. On the other hand, if the SNR margin is negative, then the transmit power or spreading factor needs to be increased in order to still be able to receive the packets. Not only does the spreading factor determine the energy required to send the packet, it also impacts the receiving downlink messages from the gateway. In LoRaWAN, after sending an uplink message, the gateway has two receive windows or opportunities to send a downlink message. In the first receive window, the downlink message is sent on the same frequency as the uplink message and is sent with the same data rate or spreading factor as the uplink message. While in the second receive window, a predefined frequency and spreading factor is used. As recommended in the LoRaWAN specification, a spreading factor of 12, which is the highest spreading factor, is used in the second window. So just to be sure to be able to receive the downlink message as it is the most robust setting. So depending on where the downlink message is sent, the energy required to transmit and receive is different. When we are able to increase the data rate, as the SNR margin is positive, we decrease the energy consumption of both transmitting and receive window 1, while changing the transmit power only changes the power during transmit. To study the effects of channel dynamics on the energy efficiency of the devices and overall throughput, we developed a LoRaWAN simulator. The energy profile of a real device is used as shown in previous slides to emulate the energy consumption of the nodes. We used a log distance path loss model with shadowing, where the shadowing denotes or follows the shadowing term follows a normal distribution. The simulator is open source and is available at the link below this slide. One of our interests was to see how we could improve the energy efficiency of our nodes. When looking at the energy per payload bit, which is here shown in the y-axis on the graph, we noticed that sending larger packets could improve the energy per bit. This effect is the same for every spreading factor, but is most noticeable when utilizing large spreading factors. And hence, we could accumulate data and send them once instead of sending a couple of individual packets. This is due to the increasing total number of headers and downlink messages required when sending only small packages. And because we send packets less frequently, the chance of them colliding is smaller, and we will thus require less retransmissions in a stable environment. However, this could not be the case when working in a more dynamic environment. To evaluate the effect of the dynamics on the system, we defined two metrics. Here, in these two metrics, or the formulas, J denotes the number of Monte Carlo simulations we've done, and N the number of nodes in the network. First, the effective throughput, or data extraction rate, is shown. This metric shows how much of the intended uplink data is received. It is defined as the ratio of unique received bytes to the unique transmitted bytes. Retransmissions are not counted in the unique transmitted byte. The second metric shows how much energy is required per uniquely received byte and thus illustrates the energy efficiency. Notable is that the lower this metric is, the better the energy efficient. It is the ratio of the total energy consumed by the node to the unique received bytes by that node. And the data extraction rate can often be improved by allowing retransmissions, while this would negatively impact the energy efficiency as more energy is spent transmitting the retransmissions. These metrics are evaluated in three different scenarios. First, when enabling both adaptive data rate mechanism and confirmed messages. These confirmed messages allow us to ask for retransmissions if the packet is not received by the gateway. Network-related data is piggybacked with the acknowledgement from the network and allows to more quickly get feedback of the ADR mechanism from the network. Secondly, when ADR is on but no retransmissions are requested, and thus the ADR feedback is less frequently provided to the node. The last case is when both ADR and confirmed messages are disabled. The effect of these configurations is investigated with respect to the payload size. Different graphs denote a different standard deviation of the path loss model. When both ADR and confirmed messages is off, the impact of channel dynamics is not noticeable. This is because the nodes do not consider the link quality and just follow a send and forget approach. While enabling the ADR mechanism improves the energy efficiency. The impact of enabling the confirmed messages, which is a top graph, which is shown in the top graph, is negligible because the negative effect of the retransmissions is nullified by the positive effect of more rapid response of the ADR mechanism. While for energy efficiency, the difference between the first and the second configuration is unnoticeable, for the data extraction rate, it is more visible. Here you can see the effect of enabling confirmed messages, as the data extraction rate is almost 100% for every channel condition. But what is most interesting here is that for higher channel dynamics, the data extraction rate drops when not enabling confirmed messages. This is due to the ADR mechanism being too late to respond to changing link qualities. One way to tackle this issue is not to overestimate the link quality, as the recommendation of the protocol suggests, taking the maximum. And if we, for instance, use a minimum selection criteria for the SNR and thereby underestimating the channel conditions. The impact of choosing the maximum over the minimum is shown by these two parameters, alpha and beta. Alpha denotes the ratio of the consumed energy per byte when using SNR max to the energy when using SNR min percentage-wise. The gray area indicates where the default SNR max is better, and the same analogy can be followed with the data extraction rate with beta. This. When there are no channel dynamics, when there are no dynamics in the channel, it is better to underestimate the channel for both data extraction rate and the energy efficiency, which is certainly noticeable for smaller packets. However, when there is some channel dynamics in the system, alpha drops below 100%, and thus the default is better. For the data extraction rate, it's always better to underestimate the channel, which is logically, as you send with a higher transmit power or a higher spreading factor, and thus is so the gateway is able to receive your message better. So choosing between SNR max and SNR min allows for making a trade-off between energy efficiency and effective throughput. To conclude, the current ADR scheme needs a more adaptive algorithm to be able for one to make a trade-off between energy efficiency and effective throughput, and otherwise to better follow the channel conditions in the propagation environment. Even for dynamic scenarios, RDR improves the energy efficiency, but for high channel dynamics, ADR has an inverse effect on the data extraction rate because it can't follow the rapid changes in the channel conditions. Future work is still to improve on the ADR mechanism as recommended in the LoRaWAN spec. Also to experimentally investigate the channel conditions, which we have done for point-to-point nodes, which you can find in the IEEE Explorer link. And secondly, or thirdly, strategies for optimizing energy efficient connectivity of IoT nodes is investigated on a project we're working on, where we're looking at sub-gigahertz massive MIMO communication to support the new wave of IoT devices. More information about this project you can find in the URL below. Thank you for listening.